Hello. Today I will be presenting dynamic programming and some common applications. So, origins and ideas. Well, it was first introduced in the 50s, and it's an optimization method applied to recursive algorithms that can drastically reduce the asymptotic complexity of a naive approach. It's commonly found in sequence analysis, such as finding the difference between two files. More specifically, think of version control, such as Git. And we're simplifying a complicated problem by breaking it down into simpler subproblems. This kind of might remind you of divide and conquer. However, the subproblems in divide and conquer are independent from one another, whereas dynamic programming is used when they are dependent. And these subproblems, we try to avoid redundant computations. Let's take a look at a very simple, common introduction to dynamic programming, which is the Fibonacci sequence. We typically start with two seed values that are 0 and 1. And I just wanted to mention that you can also derive the Fibonacci sequence from the Pascal's triangle. Now let's take a look at the iterative implementation. This is actually big O of n, right? Because we are simply traversing our array once. If we look at the recursive implementation, we can see it is much more elegant, and we might say this is the better approach. However, this is a naive thought, because when we actually look at the graph of recursive calls, first say fib7, which is fib6 plus fib5, and this is fib5 plus fib4, we will actually see that we are performing a lot of redundant computations, and the asymptotic complexity is actually exponential, or better yet, 2 to the n, because we can see that, for example, fib4 will be recomputed here, will be recomputed here, it will be recomputed there. So this is actually very slow as n increases, but we can use dynamic programming to give us the same complexity as the iterative approach. We will add memoization. What it means is we're simply storing the values we already computed. So we are allocating an empty array and making sure that we're not doing the same computations over and over again. So dynamic programming can be broken down into 4 main steps. First, note that all dynamic programming problems satisfy the overlapping subproblem property. So these subproblems are dependent from one another, and we note a recursive substructure. Second is to determine all the states and the transfer equations between the states. And this is also the hardest part. A state can be thought of as a set of parameters that uniquely identifies the solution of this particular subproblem. It can be an index or the size And we will see in our next example more specifically what these states are. Step 3, we will be constructing a transfer equation. And for step 4, we will add a bottom-up table or a top-down memorization, depending on how you're approaching your solution. So let's take a look at the most common example, which is longest common subsequence. If we were to brute force the solution, we would have two arrays, in this case x and y, and we're going to want to find and compare all possible subsequences. So all the subsequences of x would be this list right here. And we're going to traverse this sequence n times, because for each of these, we will have to go through our y. Let's take a look at a recursive implementation. So this is using a 1-based index. If our example was x equals ABC, and we have y equals AEBDC. This algorithm will, and I and j will be initialized as the size of x and the size of y. So I will be the index for x and j will be the index for y. So our first call will look like this. Size of x is 3 and size of y is 5. And if I equals 0, that simply means that we are outside of our array. We just return 0. Here is where we will actually compare these values. And the first ones we compare are C and C. These are actually equal, right? We will enter this if loop and compute the LCS of I-1 and j-1. And since they're equal, we will be adding 1. So 1 plus LCS of x comma y with 2 and 4 as our indexes. And that will be B and D. These are not equal. We will be going to this else, and this will be the max of LCS I-1 comma j and LCS I comma j-1. So this one will remain B for x, and for y we will be at B. Okay, those are equal. So then we subtract 1 from both indexes and we get A and E. We will go to the left, A for x and A for y. For our bottom-up approach, we will be looking at the same example. Let's put x as our rows and y as our columns, and we will be filling those extra rows and columns with zeros. And now bottom up works from 1 to m, and j will be 1 to n. So note the difference as we go in incremental order. Intuitively, it's very similar. We will be comparing these two values first. We notice that they are equal. It'll be 1 plus I-1 comma j-1 is outside of our array, so that will just be 0. And that is why we filled in those first rows and columns. 1 plus 0 equals 1. And now we increment j, and we will be looking at AE. Well, they're not equal, so we'll get the max value of I minus 1 comma j and I comma j minus 1. But we can easily see that I is 1, so that'll be 0. And j minus 1 we just computed, so it'll be that value at AA, 1. And we keep moving forward to AB. I minus 1 is 0. J minus 1 will be the value at AE, 1. AD are not equal, 1. AC. And now we increment our I index. So I will equal 2 and j will equal 1. BA is not equal. So we will be getting I minus 1 comma j. J is equal to 1 and I minus 1 will equal 1. LCS of I or of 1 comma 1 we computed earlier, and that goes down to 1. BE is not equal. Same process. We're currently at 2 comma 2. 1 comma 2 is 1, and 2 comma 1 we just computed is 1. The max value between this one and that one remains 1. BB is now equal. So it's 1 plus, well, we're currently at 2 comma 3, so we have to look at 1 comma 2. That's this value. So 1 plus 1 is 2. BD not equal. We're currently at 2 comma 4. So 1 comma 4 is 1. And 2 comma 3 we just computed is 2. Max value between those is 2, etc. Now we're at C comma A. They are not equal. This is 3 comma 1. 2 comma 1 is equal to 1. And 3 comma 0 is equal to 0. So this will be 1. CE 3 comma 2 not equal. Max value between 2 comma 2 and 3 comma 1. 2 comma 2 is 1. 3 comma 1 is 1. We're still at 1. Okay. And now, which is 3 comma 3? Not equal. So we look at 2 comma 3. Well, that's 2. And 3 comma 2, that's 1. Max value is 2. CD 3 comma 4. 2 comma 4, that's 2. And we look at 3 comma 3. Just computed. Max value between 2 and 2 is 2. And then C comma C is equal. And we will be looking at 2, 3 is 2, 3. So this is a result. From all these links, we can actually derive the largest common subsequence by traversing this list backwards. Meaning we start at CMN right here. And we will be looking for whenever we see an increment, or when Ci, comma j is equal to Ci minus 1, comma j minus 1 plus 1. And if we circle all the values that have incremented, and we can see we get C goes to B, which goes to A, which is in reverse. ABC is our longest common subsequence. To recap, when can we use dynamic programming? Well, if the optimal solution involves solving a subproblem, and those subproblems are dependent from one another, or in other words, there is an overlap of a polynomial number of subproblems. Now, dynamic programming is actually hidden in plain sight. Distra's algorithm is another classic example. It reuses prior computations to discover the shortest path between two nodes. You will also see it in artificial intelligence, machine learning. PyTorch is great for writing dynamic programming. So the keyword is overlapping subproblems and optimal substructure. When you execute quicksort or merge sort, you're recursively breaking down your array into smaller pieces, but they do not overlap. You never operate over the same elements of the original array. So that is not an example of dynamic programming, because there's simply no reuse of previous calculations. But there are many problems that do involve performing the same calculations over these overlapping subsets, and they have this useful characteristic that an optimal solution to a subproblem can be reused when computing a larger problem. So I encourage you to look at these examples on your own and see other examples on Wikipedia, because it is also widely used in bioinformatics for such as sequence alignment, protein folding, RNA structure prediction, and DNA binding.